Hi. Today's topic is probability. Some people hear the word probability and say, oh, that's mathematical, and get a little tense. Do not in any way consider this, what we're going to talk about, probability, mathematics. It is simply simple stuff. Let's go do it, and you'll see what I mean by simple stuff. We're going to ease in slowly. An outcome is the result of a happening. If I do something and a result occurs, perhaps a number, we call that result an outcome. Maybe if I roll a die, the outcome is a 2. Roll it again, the outcome is a 6. Flip a coin, the outcome is a tail. Flip it again, the outcome might be a head. Pick a number from 1 to 10, I might say 7. The outcome would be a 7. The outcome is simply the result of a happening. And usually in statistics, it's usually numerical, but it doesn't have to be. Frequently, we have equally likely outcomes. And though we saw that once before, equally likely outcomes occur when each outcome has the same chance of occurring. If each outcome has a... What do we mean by chance? It's one of those terms that I'm not going to define because it has to be something we have a feeling for, we understand. And I think most of us understand when we say things are equally likely or there's an equal chance of this occurring as that occurring. We have a feeling for it. We know what it means without being told how to define it. So we're going to say equally likely outcomes is when each of the possible outcomes, and we can think of if it's a coin, heads and tails. If it's a die, 1, 2, 3, 4, 5, 6. If all of these outcomes in an individual flip of the coin or roll of the die has equal opportunity, we say they're equally likely. And usually when flipping a coin, there's really no reason, although most people pick heads when you flip a coin, there's no reason for heads to be more likely than tails. The coin is balanced. And so we say that heads and tails are equally likely. Rolling a die, 1, 2, 3, 4, 5, 6, we say it's equally likely. In actuality, there may be a slight bias because of the way the thing was manufactured. One side might be a little bit heavier than the other. However, we're not going to quibble about that, and we'll say they're equally likely. However, not all outcomes are equally likely. What if I had a box? In my box, there were 5 blocks of wood, 3 of them colored red, 2 of them colored blue, and I were to pick a block out. Well, you say, well, there's no reason this block should be picked more often than that block, or this one, or this one, or this one, so the blocks are equally likely. That's quite true. The blocks are equally likely. I wouldn't argue with that. However, most people think in terms of picking a block out and looking at the color. Not at which block it is, but at its color. And the colors are not equally likely. We should have a feeling for that. In fact, if I asked you what the chances are, you'd probably say, well, red has a 3/5 chance and a blue has 2/5 chance because there are 3 out of 5 of the blocks are red and 2 out of 5 of the blocks are blue. The colors red and blue are not equally likely, and the chances of their occurring are not the same. They don't have the same chance of occurring. And P is just here representing the proportion of time. Let's imagine that I have this box with the 5 blocks, and every minute I come back to the box and I pull out a block without looking. And this time it's red. And I throw that block in, and I fish it around. A minute later I come back and I pick out this one. And then put it back in. A minute later I come back and I put out this one. A minute later I come pick out this one again. And I do that over and over again. The proportion of the time that I get red will be 3/5 of the time, approximately. And the proportion of the time that I get blue will be approximately 2/5 of the time. So this P stands for the proportion of the time. Now let's define an event. An event is a complex result. And by that I mean it's a group of equally likely outcomes. In fact, the example, red block, is a very good example of an event. We said the blocks were equally likely, but red block is made up of the 3 red blocks. There were 3 red blocks in there. These 3 made up the event red block. Meaning if I picked one of them, any one of them, this one or this one or this one, I would say I succeeded in picking a red block. So a red block is not a simple outcome. In this case, it's not simple at all. It's any one of three outcomes. So it's a group of equally likely outcomes, or a complex result, meaning it could have more than one outcome making up the event. Now, so far, I doubt that there's anything that you will say is too mathematical for you. You will say, yes, sure. I mean, let's go on with it. Let's get to something harder. This is trivial stuff. Well, I'm happy to tell you that it's over. You already know what probability is. Probability is simply the proportion of the time that an event will occur. What is the probability of picking a red block? The probability of picking a red block was 3/5. What's the probability of picking a blue block? The probability of picking a blue block was 2/5. So we already know the meaning of probability because it's very easy to figure out the proportion of time something will happen when it's made up of equally likely outcomes. Okay, let's play flipping a coin. I have a coin and I flip it. Actually, I'm going to talk about flipping two coins or flipping one coin twice, once and then once again. What are the events we could be interested in? Well, if we flip two coins, or we flip a coin once, the events are the following. I could flip two heads, or I could flip one head, or I could flip no heads. So in two flips of a coin, I could get two heads, or I could get one head, or I could get no heads. Those are the interesting or useful, or if we're betting in a game, those would be the things we look at. Those are the events. And we're interested in the proportion of time that those events would occur. That is, the probability that those events would occur. Or, simply stated, the chances that those events would occur. The outcomes are not those events, because I think we all realize that you're not just as likely to flip two heads as one head. The outcomes of flipping two coins are simply heads, 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 tails, tails, heads, tails, tails. And now, is there any reason that you can think of why one of these pair of heads and heads should occur more often than tails and tails, or heads and tails should occur more often than tails and heads, or even heads and heads? If the coin is balanced, each of these possibilities, and these are the only possibilities that occur with two coins, or flipping one coin twice, that those are equally likely. So the outcomes, we can call these outcomes, even though they're a pair of things. We imagine flipping the coin twice and only looking at the results of two, one after the other, or flipping them two coins, one on the left, one on the right, and looking at what they are. In any case, these are the outcomes. They're equally likely. We can use these outcomes to build up the events and therefore find the proportion of time, or the probability, that those events would occur. Let's do it. Two heads. Two heads, the only event in two heads is head-head. It's the only way I can get two heads. I say I have two heads only if both coins come up heads. One head. Well, I say I have one head if I flip a head and then a tail, or a tail and then a head. So there's really two equally likely outcomes in the event one head. One head is made up of two outcomes. Two heads is made up of one outcome. This should occur twice as often as this occurs. One head should occur twice as often as two heads. So if you flip two coins over and over and over again, and just look at how often one head occurs and how often two heads occurs, that is, one head and not two, and two heads, you will find that one head and not two occurs twice as often as two heads occurs. How about no heads? Tails, tails, the only way to get no heads. And so this should occur as often as heads, heads. You'll get as many tail, tails as you get heads, heads, but you'll get twice as many one head as you get tails, tails, or two heads. And if you want to combine two heads and no heads, you get the same number of two heads and no heads as you get one head. The probability, or the proportion of time that you get two heads, is 1/4. If they're equally likely, then 1/4 of the time you get this, 1/4, 1/4, 1/4. 1/4 of the time the event two heads will happen. The probability of flipping two heads in a row is 25%, 1/4. One head. What's the probability of flipping one head with two coins? Exactly one head. 2 out of 4, each one is 1/4. 2/4, 1/2 the time you will flip one head. 1/4 of the time you will flip no heads. That is, you'll get two tails in a row. So figuring probabilities is not difficult at all. It's kind of trivial. Let's look now at a deck of cards. I'm not wanting to make you gamblers, but I do want you to sort of know what a deck of cards looks like because we'll be referring to it. You'll notice that there's an ace, whoops, on this side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. And then there's suits, spades, hearts, clubs, and diamonds. There's 52 cards altogether. There's 13 in each suit, 4 suits, 52 cards. That's what a deck of cards looks like. We call it a bridge deck or just a deck of cards. And we're going to be using this and thinking about it. I want you to sort of, if those of you who don't know what a deck of cards is, now you know. Okay, let's look at this deck of cards. Full deck of cards. 52 cards. What proportion of the cards was clubs? Well, 1/4. 1/4 of all cards were clubs. And so we can say that, easy enough to say, well, if I were to pick cards one a minute forever and ever, 1/4 of the picks would probably be a club. About 1/4, because 1/4 of them are clubs. I could also say, well, there are 52 cards, 13 of which are clubs. So picking many, many, many times, 13 out of each 52 will give me clubs, but 13 52s is 1/4. I prefer looking at it this way, at each card as an outcome. Think of each card as an outcome. And there are 13 of the 52 which are clubs, and each one has a 1/52th chance of occurring, so 13 52ths is 1/4. Now let's take an incomplete deck. And by incomplete deck, I mean take this deck of cards and say, straight up, yeah, okay, and let's just get rid of one of these cards, like that one, say. I don't mean to replace it with a joker. Let's just replace it with nothing. It falls out of the deck, and it's not there anymore. So now there are 51 cards. There are only 11 spades, and 12 of the, 13 of the, sorry. There are 12 spades and 13 clubs, hearts, and diamonds. There are only 3 aces, but there are 4 of each of the other kinds. Okay? If that were the case, then what is the probability of clubs? Well, there's still 13 clubs. There were only 12 spades, but there are still 13 clubs, but there are 51 cards. If each card is equally likely, then each card has a 1/51th chance of being picked. 13 of those picks are clubs, so the probability of clubs is 13 51s. Not quite what it was before. It's slightly different. You cannot say, before we said the clubs was 1/4 because all the suits were equally likely, but here the suits are not equally likely. We cannot talk about suits as if they were outcomes. We must talk about cards as outcomes, and 13 of those cards are clubs. Okay, now, you have what's called the classical approach to probability. It's by far the easiest approach. You should use it whenever you can. Someone says, what's the probability of a boy being born? You say 1/2, figuring boys and girls are equally likely to be born, and a coin flipping 1/2. And everything is fine there. And it works great. You don't have to do anything. You just think about it, and you'll come up with the answer. Sometimes, however, we don't believe that things are equally likely. The coin isn't balanced. Or, even more particular, the chances of a boy being born are more likely than the chances of a girl being born, because people who've watched births over the years have found that there are a little bit more boys born than girls. Well, how do you find the probability of something happening then if it really isn't balanced? If there's an unbalance, you have an unbalanced coin, you have an unbalanced die. You can't just say 1/6. You can't go look at cards and, well, with cards they're either there or they're not. There's no unbalance. But in a coin you flip it, heads and tails are equally likely. What if the thing is balanced so that the tail is heavier? You come up heads more often because the head will sit up on the top. How do we do that? The way to do that is to just watch the proportion. Remember the proportion of time. A probability is the proportion of time something will happen. Well, let's say we don't believe that boys and girls are equally likely. We want to find the probability of boys and girls. So we go to the hospitals and you watch children being born and find the proportion of time that boys are born. And if you've taken 100,000 children born, you might find that the proportion of boys in your sample, in your 100,000, is 51% rather than 50%. Well, if that's the case, then I'm going to say I believe the proportion of boys is approximately 51%. All right? So you would flip the coin 1,000, 100,000 times, as many times as you could, and find the percentage of heads that came up. And if it came up 51, you'd say the probability of heads is 51% rather than 50%. That would be the frequency method. That's the frequency method. And it's used when equally likely outcomes are not available. If they're available, we use them. Heads, when someone asks you the probability of a boy, don't say 51%. Say 50%. Say a half. That's the first way you go. If they want you to fine-tune it, then you say, well, I'll have to go and check it out. But use the equally likely outcomes whenever you can. But if they're not available for things like unbalanced situations which do not have any possibility of being equally likely, you would simply use the frequency method, which says measure the proportion of time that the event occurs. Measure the proportion of time that the event occurs over a very large number. And that won't be exactly it, but at least it'll be close. You could say it's approximately. If I got 51 out of 100, I could say it's approximately 51%. But I know 100 is not a very large sample, and 51% is only approximate. If it was 1,000,000 and I got 51% out of the 1,000,000, I'd be a lot happier with my guess at 51%. Okay? And that's it for the simple concept of probability. See you next time.